Hello, I'm Yuwei. I'm currently a PhD student at the University of Tokyo. Today, I'm going to talk about our research on network flows-based malware detection using a combined approach of crawling and deep learning. Here's today's agenda, followed with a brief introduction of background. The section of methodology will be broken down to the three parts: data collection with web crawling, network flows-based segmentation, and feature extraction, malware detection based on deep learning. After that, we will look into model optimization and evaluation results, and finally give out the conclusion. For the background, the pandemic of COVID-19 is accelerating the digitalization in many walks of society, along with more and more devices and people connected to networks. Phishing through methods such as the malicious websites causes unintentional disclosure of private information to an attacker. Detecting such malicious activities needs the enormous human effort and expertise. Besides, malicious patterns are hidden within the network traffic data, usually difficult to recognize for human experts. In this research, we propose a deep learning approach to detect malware using the data collected from web crawler that systematically sends requests to benign and malicious websites on the internet. After applying procedures to segment the network flows and extract the features, we use these extracted high-level network traffic features to train a deep neural network to recognize benign and malicious flows. After training on these network flow features, the system could detect malicious traffic flows from malware URLs adaptively based on the hidden patterns of the client-server interaction. Finally, we evaluated our malware detection approach against various metrics, including the precision, the recall, and the F1 score. The detection results show that the system can learn to discover high-level insights from the network flows. Different from formal research focusing on the lexical analysis of data, we aim to detect malicious websites by actively sending requests to the websites and then extracting malicious pictures from the real-time network flows between the client and the server. We launched our web crawler to visit 1,400 benign URLs and 1,400 malware URLs from the Canadian Institute of Cybersecurity by systematically sending requests to these websites. These URLs were all confirmed to be valid at the time of the experiment. At the same time, a workstation is deployed in charge of collecting real-time network traffic data in the network by using the tool called the TCP dump for further analysis. Additionally, we set a fixed time window between sending the request to ensure that sufficient traffic could be harvested in the interaction between the client and each site. We use the tool called the NF string to perform traffic flow analysis. After converting the collected packet capture from the local area network line into various flows based on the network interface, the protocol, and the IP or port source destination, we ended up with network flows, each of which was represented with a 12-item feature vector. Then using another tool, DPKT, we further extracted flows related to crawling targets, especially the flows with the source or destination IP address from the URL's IP addresses in the dataset were selected as a flow feature dataset. Finally, we obtained the 2,472 benign feature vectors and 5,109 malicious feature vectors, respectively. The selected features of network flows are shown on the right-hand side. Besides, we analyze the application types of these network flows used by the servers of the URLs. We found most malicious URLs, the HTTP protocol based, whereas the benign URLs were more likely to adopt the TLS protocol, which is often provided by trusted source. Let's move on to the next topic, malware detection based on deep learning. We realized that the deep learning using a fully connected neural network with multiple dense layers or fully connected layers using the extracted flow features as the input and the UL types as the labels, where 0 represented benign and 1 represented malicious. Besides, as pre-processing of the input, we employ the L2 normalization to rescale the input attributes to a number between 0 and 1. The activation function at the hidden layers is redo. The sigmoid function is used at the output layer for narrowing the output into the range of 0 to 1. In addition, the applied loss function for this neural network is cross-entropy. To optimize the model structure, we experimented with various hyperparameters to effect the performance changes, including the composition of hidden layers and the learning rate, learning function, and the batch size. The batch learning method was applied where the dataset was partitioned into the small chunks for training purpose. We compare the performance of 4 different learning functions, the SDG, the momentum, the AMSprop, and finally the ADAM, both with the various learning rates shown in this table. To evaluate the performance of our model when applying the different combinations of hyperparameters, the precision, recall, and F1 score form the base of our matrix, where the precision is the fraction of relevant network flows successfully classified among all flows in the validation set. The recall is a fraction of relevant network flows successfully classified among existing relevant network flows. And finally, the F1 score shows a balanced evaluation result based on the computed precision and recall. As a result, a total of 320 combinations of the various hyperparameters were used to train the model. Besides the early stopping strategy was used when we train the model to prevent the overfitting. By comparing the batch validation F1 score for the last 5 epochs, we evaluated the performance of the model when applying these various combinations of hyperparameters. We visualized the performance results when applying different combinations using the heat maps. Here shows a sample when applying the ADAM as a learning function with different learning rates and batch sizes. Finally, it shows that a 4-layer artificial neural network model shows the best performance when the learning rate is 0.001 and the batch size is 16. For the evaluation, we conducted the performance evaluation against the various metrics, including the precision, recall, F1 score, and the loss. As you can see in the graph on the left-hand side, the early stopping strategy was used to prevent the overfitting. A situation where the training loss keeps decreasing while the validation loss keeps increasing. By monitoring the variance of the recent 5 epochs validation loss rates, we could train the model with more balance between the training performance and the validation performance. As a result, the training stopped at the epoch 43 because due to the early stopping strategy. At last, the detection scheme with optimized deep neural network achieved a batch validation precision of 0.88 a recall of 0.972, and the F1 score of 0.924. Another important validation aspect is the explainability of the deep learning-based, DL-based decision-making. To achieve this goal, we can extract weights of the first layer from the trained artificial neural network. Then we computed the average of the weights connected to each node at the input layer. By using the impact factor function shown in this equation, we further converted them into the impact values, which represent various flow features' impact on inference of the model. The absolute is a function to obtain the absolute value of the large weights, and the time is a rescaling of the logistic sigmoid such that its output will range from the 0 to 1 with no negative inputs. On the right-hand side, each network feature's impact factor to the final decision is visualized. As we can see, the features of the app protocol and the destination ports had more impact on the inference of the model compared with the other features. Now, if we look to the different application protocol types once again, used by the different malicious and benign websites, the great difference in the distribution proves that the deep learning-based model has already acquired the knowledge about the difference and stored the knowledge within the networking of various neurons. That explains the explainability of the deep learning-based detection system. To conclude, we presented a network flows-based malware detection mechanism based on web crawling and deep learning. A dataset consisting of 7,581 feature vectors of network flows was built for training a deep neural network. A comparison of the artificial neural network model's performance when applying various hyperparameters combinations was conducted by using the F1 score. Finally, the optimized deep neural network was employed, showing a validation F1 score of 0.924 for the detection. In the future work, we will extend this effort to a collaborative scheme where networks share intelligence on the malware detection in a federated learning architecture. That brings us to the end of this presentation. I'd like to thank you for your time and attention today. I'd love to answer any questions you may have now. Thank you.